Neurips 2024, Part 9, Embodied Agent Interface, Benchmarking LLMs for Embodied Decision Making, Percy, Liang, and others. This is a really, really important paper because what it's doing, it's trying to standardize what robotics is supposed to do and how it's supposed to be executed and how it's supposed to be evaluated, which in my opinion is the holy grail of any kind of software development project. It's to build a useful evaluation metric on which we can iterate. If we lean back for a second and we look at any kind of software development, whether it's robotics, whether it's text-based or physics-based, you always have the same problem, right? Because software development is, if you will, it's an empirical technology or science or both. There's no closed-end formulas for how to build a robot that can work in your kitchen. It's not like you can program in a closed-end form what the optimal robot would look like. The same way you can't program the most optimal self-driving car. It's an iterative process. If you look at some of the more successful projects like the Tesla FSD or this large language model development by OpenAI and others, what they've done over the years is develop a form of iteration that allows the models to continuously improve against certain specific goals, which is those evals. So what the industry calls eval is really, okay, what are the benchmarks? Okay, if we look at humans, we send our kids to school and then we grade them, and that's an eval, right? So we try to say, at least that's what we try, sort of in a objective way, we try to say that kids with better grades turn out to be better for work, better citizens, better family members, and things like that. That might be wrong, but it's the eval we're using. Other people use different evals. Religious people have their own evals, and they develop people that succeed in that kind of system. Communism had their own eval. They came up with people. So whatever system you choose, whatever eval you choose, I could even go further. Let's say if I look at Reed Hastings' book about No Rules Rules, when he said, look, culture at Netflix or culture in general, the company, is what gets you promoted and fired, right? That's what culture is. And culture is the product of eval, because what gets you promoted or fired is really, that's the result of the eval. So back to this paper. So what these people are trying to do is really, try to set up benchmarks for tasks and goals, and also formalize this. They're using what's called the LTL, which is linear temporal logic. That's a formal language to express a sequence of states and transitions and actions. So you have a state, you have a transition, you have an action. Let's say if I tell a robot, go fetch me a bottle of water, there's a state, which is the state that I'm in and the state that the robot is in. And then we have the transition from the state that I'm in and the robot is in towards the end goal, which is me having a bottle of water. And there's a lot of intermediate states that need to be taken into account. For example, the robot might have to go from A to B. It might have to open a fridge, take out the bottle, open the bottle, give it to me. It might not have to open the bottle. But if we look at, again, generally, I mean, this is a problem that humans also have, right? If I tell a person, go clean my room, they might have a sense for what that means. But if I tell a person, go fix my closet, they might not know exactly what that means. What does it mean, fix your closet? Like, should I, one of the examples that the authors are using in the paper is the state description. For example, clean the fridge. Well, what does clean the fridge mean? Does it mean, is the state of a clean fridge just simply a fridge with no stains? Or does it imply that the fridge is not wet? Is it possible that maybe we have different types of stains, certain stains that we might tolerate, that we might still consider the fridge clean? What does clean actually mean? And when does the robot know it's clean? So those are the kinds of things that the authors are trying to standardize. So what that means is they're not necessarily trying to decide what is and what isn't. They're just trying to find standards. They're using existing evals and existing techniques, and they're kind of combining them. But most importantly, though, what they're doing, in my opinion, is apply this LTL to the problem. And that is a formal language that, again, is, how should I say, it's a language that has in it, it's like a programming language that particularly takes care of the problem of state, transition, and goals and actions, right? So you have a state, you have you state a goal, go fetch me water. Then you have the state, where are you, where's the robot, where's the water? The robot needs to understand how to go get the water, which is a bunch of actions which have subgoals, substates. So for example, the robot needs to go find the water. How does it do that? So does it just do a random search? Does it have certain semantic understanding? For example, fridge might mean water. And that's actually where LLMs are really good at. So some of the things LLMs are very good at, for example, understanding the water might be in the fridge. What LLMs are really bad at, according to the authors, is to understand that they need to open the fridge to get the water out. So there's some semantic understanding that we humans actually take for granted that LLMs still need to learn, which is really interesting if you think about it, because maybe you've noticed that sometimes when you go, let's say when you travel, one example, like let's say you're Italian and you're used to drinking espresso, and you go to your typical cafe bar and you get your espresso, and then you go to a US or China or a place like that and you order your espresso, and they might give you a very big cup with very little coffee in it, an espresso. They might not give you sugar, they might not give you a spoon. So there's some obvious things that as an Italian you expect when you order an espresso that you're not going to get in Indonesia. And that's because the cultural understanding, the semantics around espresso in Indonesia are very different than the ones in Italy. Vice versa, if you order a chicken curry in Italy, it might look very different than the one in Indonesia. So I think that's kind of what this paper is trying to standardize for robots, because the same way we humans have different semantic understanding. Like, we understand roughly where we are, and we understand our transitions and our goals. Like, let's say, get me an espresso. The person in Indonesia understands what it means to get somebody an espresso, but they might forget certain steps or not know certain steps that are, from the perspective of the user of the espresso, totally, like I need to have a spoon and sugar. You can't give me espresso without sugar. They might not understand that. So those types of things, LLMs are still not very good at. It's the best we have, though, right now to solve that problem. Now, to me, this kind of opens a Pandora's box in the sense that we have this conversation whether we need to have priors or not when we train AI. And people are converging now to the fact that, well, we can use LLMs as priors because they really have a lot of knowledge already embedded in them. So why don't we use them to teach our robots how to do stuff? But then this paper shows that there's still a lot of open questions, and particularly when it comes to action, because LLMs are not trained on action, and LLMs are not trained on goals, and LLMs are certainly not trained on physics. So a robot might understand that it has to go from A to B. It might even understand that it has to go up and down the stairs, but it might have no clue that going up the stairs is much harder than going down the stairs, or maybe even vice versa. It's hard to go down the stairs because of balance issues. So there's a lot of things that the robot hasn't been trained on. And if we use now priors from LLMs, which aren't trained on physics, that might go totally wrong. So the question then is, well, shouldn't we just do end-to-end learning without LLMs? In other words, should we just throw the LLMs out of the, and train end-to-end with lots of data and general models? Which brings us back to the bitter lesson, Richard Sutton, right? We shouldn't try to teach our robots the way we think, because we don't quite understand the way we think. Imagine if you taught a robot how to ski, right? This is a famous example, right? Lots of people that are very good skiers or tennis players, they're horrible teachers And that's because they don't know how to explain to somebody else what they know. And I think that's kind of what this paper is alluding to, that a lot of LLMs are exactly like that. They might have knowledge embedded in them. They might even be able to sort of conceptually understand what it means to fetch water, but they can't do it. And now we should teach our robots how to fetch water, and we're trying to use this compressed knowledge from LLMs, when in fact, maybe it's better we just let them experiment over many, many trajectories how to fetch water. Now, that is a philosophical question, but one thing we need, no matter what kind of models we apply, one thing we're going to need desperately is we're going to need evaluation. We're going to need evaluation because if we want to iterate around models, we need to understand when they're wrong, and we need to understand how to fix them. So we need to have a transition function and an eval and an improvement function and some sort of goal function. So all of these things have to be standardized in one way, and that's what this paper is, in my opinion, assuming. So some of the findings, the links in the show notes, so I'm not going to discuss now. It's a very long paper, very interesting paper, but again, one of the really interesting things is, for example, predicting tasks. So the question, open the fridge, right? If you tell a robot, open the fridge, should you just give it a state, a desired state, which is open the fridge, and then let the robot figure out what that actually means, which means open the door of the fridge. It could potentially also take the fridge and turn it around or something like that. So open the fridge is one problem. And then we could also just say, okay, go to the fridge and open the door. So we don't need to specify what open the fridge means. We could just specify what it takes to get an open fridge. Those are sort of the, they also find out that LLMs miss out on trajectories. For example, they forget that open the fridge to open the fridge to fetch water. So they might understand that water's in the fridge. They go to the water, they go to the fridge, but then they don't know how to actually get to the water because the fridge is closed, and somehow that prediction that they need to open the door to get to the water gets lost on them. Now, I don't know why that's the case, and that's a whole different conversation for theoretical computer science, why models have a certain tendency to be right in certain things and totally wrong in other things. But back to the paper, I think one of the more interesting things also that they're solving, which is sort of a typical reinforcement learning problem, which is the problem of sparse rewards. Right? Again, if we take the robot that's going to go fetch me water, right? I can certainly reward the robot eventually once it gets me the water. But what are the sub-goals that I should be rewarding? What's the reward function that the robot should be following on that trajectory? And in order to solve that problem, they're using LTL, so linear temporal logic, and specifying the point that there is a state, there is an action, there's a transition, so there's a state, transition, action, state, eventually goal. And how do I know that state A is better than state B when I'm on the path to the goal? How do I deal with sparse rewards? So that's another big problem in robotics. Again, like in the virtual space of large language models, you could argue that you can have many trajectories and then sort of statistical averages maybe over the best trajectory. But in robotics, you can't have the robot do 50 things and then eventually get to the bottle. Like, you have to be more specific about what it means to fetch a bottle. And I think that's what this paper is aiming to do. I think as a summary, it's a very big paper, so it's a choice between me giving a 2-hour presentation about this paper or doing a 15-minute summary, and I chose the latter because that's the format of this podcast series. So please read the paper, and I apologize for any misunderstandings. But my conclusion here is that fundamentally what this paper is trying to do is to standardize what it means to formulate a task, to have a goal, to decide which actions to take in order to get to which states, in order to get to the final goal. This episode is also part of our Foundation Models for Embodied Decision-Making Agents series. This is part 24. So we have part 24, we have also part 9 of Neurips 24. So this paper fits in both buckets, but fundamentally what it's trying to do is build a foundation so robotics researchers can use those benchmarks to iterate faster and also compare results to each other. This also improves reproducibility. So in the true sense, what Percy Liang and others are doing here, and that's what Percy Liang is, in my opinion, very famous for, is trying to standardize and benchmark models so other scientists can use this as a sort of springboard to improve their models. Thank you.